soften it, and the method, and this is one of the last. This is, I think, the last question on your, I guess, the hardness part. Asking you, well, probably how much lime and soda would you need to soften the hardness that you got using the selective method. And that makes sense because I said right, the Edwards aquifer is typically mostly calcium. So the cheapest thing to do is just add enough lime and soda ash. Just add enough chemicals to address the calcium only, because magnesium really isn't contributing that much to hardness. Okay? And this is the method that you use to do that. So from those, this is from that initial balance, the raw water bar chart that we had. And because we're not really going after any magnesium, we don't need to consider it. We're just looking at the calcium distribution, right? And the carbon, we have to consider carbon dioxide because it'll accept the softening chemicals. It'll react with the softening chemicals. Right? And so, in terms of, this is from the previous distribution, right? From 11.6. We've got calcium associated with carbonate, so that's the carbonate hardness. And we've got calcium associated with sulfate, and that's the non-carbonate hardness. And we need to know the difference because that will determine either the lime or the soda ash. So we determine the milli equivalents, right? Concentration divided by the equivalent weight of the species. And then we apply either lime or soda ash and determine a total amount in terms of milli equivalents that we need to add. So for the lime, right, the lime's going to address the carbon dioxide and the carbonate hardness, calcium associated with the carbonate species. So we do 0.4 and 2.3 gives us 2.7 milli equivalents of lime that we have to add to soften. For the soda ash, the sodium carbonate, Na2CO3, and I've got these up here. Here, let me finish this. We're gonna use that only for the calcium, to remove the calcium hardness associated with the sulfate anion. So that's non-carbonate hardness. Okay? So that'll give us a total in terms of equivalence. Okay? Then they go on, and all I'm saying here in this note is that you can get the equivalent weights from that table in the chapter. Then they go on to, they use that conversion to get it in milligrams per liter mass concentration of lime, and then convert it to pounds, because in reality you'd be adding this material in pounds, right? Your actual conditions are flow rates in million gallons a day, and an addition of chemicals in pounds, not in milligrams. Okay? So going back to this, just for a little bit better understanding. So the lime is either calcium hydroxide or calcium oxide, and this is quick lime. Okay, but it's easier to see with the calcium hydroxide. The hydroxide raises the pH to get that precipitation to occur, but it also provides the calcium, right, for your carbonate reaction. Okay. It's mostly the hydroxide that raises the pH to go from bicarbonate. I don't have that. To go from the bicarbonate anion to the carbonate anion to combine with the calcium to form that solid material that's precipitate out. soda ash provides the carbonate for the non-carbonate, right? Because you've got, right now you've got calcium associated with sulfate, and that doesn't precipitate. But if you add soda, sodium is soluble. It's a replacement reaction. So carbonate will replace sulfate, and that'll form calcium carbonate, and that'll precipitate out, and that's your non-carbonate hardness softening mechanism. Okay. And then once you add these chemicals, 2.7, 7 milligrams per liter of the quicklime, 6 milligrams per liter of the soda, then you get this bar chart. So now all you're left with is 0.6 calcium hardness. So you've removed most of the calcium. You've left magnesium in. You didn't really address that, right? But now sulfate, right, is the major anion because you removed most of the carbonate. So what you're left with is a little bit of calcium hardness, calcium carbonate, and more magnesium non-carbonate hardness. Okay. So here's and if graphically, here's what we started with, right? Significant portion of calcium and carbonate. And so what we did, right, we just removed all that with that lime and soda ash. Actually, we removed more. We removed, with the lime, we removed the significant portion of calcium carbonate, calcium bicarbonate. Okay? Now, there's going to be a residual that you can't get. We removed a significant portion of calcium carbonate with the carbonate hardness with the addition of lime. We removed a little bit of the calcium sulfate with the soda ash. So that was the calcium non-carbonate hardness. What we're left with is the magnesium, because we didn't try to address that, with magnesium sulfate, so magnesium non-carbonate hardness. So that, right? That's so you can see how much you lost. So that's all we did. We softened it. And so back to the board. If you use example 11.7, that's the one we just went over. The sum of the milli equivalents, which we determined here. Notice there's an error in the book. It should be 1.2, not 12. So when I say sum of milli equivalents, that's what I'm talking about here. The sum of the milli for lime and the sum for soda ash times the equivalent weight of the calcium of the quicklime and the sodium gives you the concentrations. Or actually, yeah, 28 and 53 gives you 76 and 64 mass concentrations, milligrams per liter. So I think that'll get you, that doesn't equal that. That'll get you the answer, I think, to that question on your lab. Okay, and you can get these from table 11 and 1. Here's the conversions, right? I was trying to do this the other day, trying to get it so it relates to each other. Milligrams per liter, you can convert either way. Right? Going to a milli equivalents, you have to get those bar charts in terms of equivalents. But you can also, if you just want to go from milligrams per liter of the compound to milligrams per liter of calcium carbonate, use the equivalent weight ratio. Okay, so that's hardness and softening, and then I think it's the alkalinity lab asks you to how much alkalinity would be used if you're considering a alum coagulation. So don't let that confuse you. Remember, you can perform these same mechanisms in the same reaction. So you can have softening and coagulation, right? Because both of them will precipitate out. The softening just takes the hardness compounds, precipitates those into something solid, and the alum takes those colloidal particles out of suspension, so both of them can grow into flock and settle out. So we're talking about alkalinity here, and now we've thrown in alum, which is used for coagulation. But this is a chemical reaction that also consumes alkalinity, right? Again, it's that pH acid-base reaction. So for this equation 1152 in your book, you've got alum added, and so for 1 mole of alum, I think this is the one I had before when we were looking at coagulation, it takes 6 moles of alkalinity to give you that aluminum hydroxide flocculent material. But there's a general relationship. So you could get to this if you did molecular weight, go from mass to molecular weight to moles ratio, and then back up to mass concentration. But in general, I don't remember what page it is. I think it's the same page as this. It says for every milligram per liter of alum that's used, it consumes a half a milligram per liter of alkalinity. Okay? But here's the equation. Does everybody kind of remember that? This is what the question's asking you. Once you've determined your alkalinity in your experiment, if you were to use that water in a coagulation reaction with alum instead of iron ferric chloride, how much would you consume of your alkalinity that you measured for a certain concentration of alum? And so for every milligram per liter of alum, you're going to use a half a milligram per liter of alkalinity. Okay. But this is the equation that relates it, and it's kind of hard to see in the equation, but we just described how your alkalinity, which is really the anion carbonate hardness, right, the bicarbonate species, is in the water. So the alkalinity is in this H2O expression right here, and it's in the form of bicarbonate, typically if the pH is relatively neutral. Okay. Any questions about that? So it's just kind of a relationship of alkalinity and hardness, and then they throw in coagulation just to confuse it. But then after that, it's just understanding which equation and converting to equivalence to get everything on the same unit. To be able to draw a chart and compare how much softening chemicals you need to address the different combinations of hardness.